Hello there everyone, and welcome back to another video from the lecture series of the course of Database Design and Implementation. To recap what we had done in the last video, or the topics that we had covered. Okay, so from just the course standpoint, we had discussed about the relational model. So we had talked about the concepts of or the properties of a relational table. And then we had discussed using the mathematical concept of determination, which led, or from which we kind of formally established the notions of functional dependency and full functional dependency. We developed the concepts of keys, or concepts of database keys. Okay, and in this we learned about different types of keys like super keys, candidate keys, primary keys, and then other keys like foreign keys and secondary keys. Okay, and this topic is essentially very important. We also learned about the integrity rules within the database environment, that each and every database and every database table that you are going to design and implement needs to follow. So we had two integrity rules. We had the entity integrity rule, and then we had the referential integrity rule. And thereafter, we talked about different relational operators. Which basically are the foundation to various SQL operations or to various data transformation techniques. Okay, you can just say within SQL, this falls within the category of data modification language. Okay, so we discussed about them, and then we also revisited the concept or the notion of data redundancy in the database environment. And then finally, we had a brief overview of database indexes. What are indexes and how they help us within the database environment. So this was from a course standpoint, but we had also discussed about the phase 1 project deliverables, about how or what are the different tasks that you need to incorporate in your phase 1 report, and we talked a bit about it. And we also discussed about installing your MySQL server and then an intro to the MySQL workbench. And specifically here in the introduction to the MySQL workbench, which is a GUI to the MySQL server that is provided by Oracle itself, so which we'll be using until we write our own GUI to interact with the MySQL server. We discussed about how to design or how to draw ER diagrams using MySQL Workbench. Okay, and we also discussed about other aspects about why you should focus on your design and how that is also helping you with the implementation, because MySQL Workbench comes with this two different capabilities, which is known as forward engineering and reverse engineering, where if you have a database design, then basically you can use MySQL Workbench to generate the data definition language SQL code that will help you implement your database environment. And vice versa, if you have the data definition language SQL codes and you would like to assess or evaluate the robustness of your database design, then you can use the reverse engineering capabilities in order to generate the ER diagram for that specific data definition language code. Okay. So moving on from those topics, the agenda of this video will kind of pick up where we left when we were discussing about how to draw ERDs in the workbench, right? And combine it with the topic of the relational model as well a bit. So our primary goal in this video is to learn about the entity relationship model. Relationship model. Okay. So to refresh your memory, when we said that we needed a data model in order to unify the different data storage and processing perspectives of the different units within your organization, right? We need a data model as a database designer to bridge all those different perspectives and to create a single universal database schema or blueprint, which will satisfy the needs of all the entities that are involved in the process, right? So for that, we said that the data model that we are going to be selecting would be the relational model. Okay, but relational model, even though it gives us conceptual simplicity, it's the foundation on which most of the processing tasks are built. So that means from the relational model, we were able to establish the concept of keys and get the help of what is known as the relational operators, which helps us in the different data manipulation tasks or data transformation tasks. It gives us the capability of database indexes, and it helps establish the integrity rules, which kind of avoids the presence of redundant data or data inconsistencies within your database environment, right? So even though it does helps us to simplify the conceptual aspect of your database design, in terms of engaging with the graphical representation of your database design, it does not provide us with any tools or arsenal in that regard, right? So that is why, if you remember our goal from a few lectures back, on top of the relational model, we will use what is known as the entity relationship model, or the ERM, where the sole goal of the ER model or the ERM is to simplify the graphical representation of a database design. So it will still kind of access some of these concepts from the relational model, specifically the concept of keys, right? And nothing else, because most of the other stuffs are functional aspects, right? But on top of that, it will introduce its own components in order to aid us with this simplification of the graphical representation of our database design, right? So just like any other components for any other data model, right? The entity relationship model, the basic blocks of the entity relationship models are entities, right? Attributes, relationship. Okay, and we are not going into constraints as such for the time being. So what we want to do in this particular video is to take a deeper dive into these three individual components and see how it plays out in the whole designing process. Okay, so there are different subcategories within the entities. There are different types of attributes that you have to take into consideration, and then there are different types of relationship. Then we will be talking with respect to the relationship strength, the relationship degree, the participation of the relationship, and so on and so forth. So that is what our goal is. So if you recall, when we were talking about this introduction to drawing ER diagrams, I said that from your palette that is there in your MySQL workbench, right? So I mentioned the fact that, so here is my trusty workbench, and I have a model all set and ready. So I mentioned here that if you look at the different relationship types, right, you have some dotted lines, and then you have the same relationship types with a solid line. So what is the difference between them? Are they representing something completely entirely different? And the answer to that is yes. And that is the reason why we will be learning more about the different components in detail of the entity relationship model, and then use that knowledge to better design our ER diagrams. Okay. So that is basically what the agenda or the objective of this particular video is going to be. So even though the chapter has this at the end, let's start with this diagram. This is a ER design of a university database system, right? And it has different components. This is basically the final conceptual design, or you can think of this as the conceptual model. So this is the conceptual model of a university database. Of course, it does not incorporate all the different functional activities or the system requirements that you can have from a university database, but it still offers a respectable amount. Okay. So now as you can see this, right, this is basically an ER diagram, an ERD using crow's foot notation. So a small remark in this direction before we talk more about it is that unless explicitly specified, all your ER diagrams or all your ERDs must be done using crow's foot notation. Okay. So what we have to ask ourselves now is that, okay, we kind of recognize that these are entities, right? And then what you have inside of this are attributes. We kind of understand this, right? And then PK stands for primary key, FK1 stands for the first foreign key within the entity. So these are kind of things that we can intuitively understand. But there are other stuffs which are in this ER diagram that is not as intuitive. Okay, and yes, of course, there are relationship labels, so you can guess what the relationship is all about between these two entities, right? But there are some things that we don't intuitively figure out, right? Some of the relationship lines are dotted, okay, whereas some other relationship lines are solid lines. You have single straight lines in some of the relationship classification type, right? You have this straight lines, but in other cases, you have this circle with a straight line, okay, instead of two straight lines. So what are these differences? What do they signify, right? And how do we systematically or in a structural fashion establish these differences and understand what they are trying to represent? So that is what we will be talking about mostly in this lecture, right? And as we go forward, we will use those concepts that we discuss, and then you will try to relate that to this final diagram and see if you can use those knowledge of our discussions about these different components, project it or extend it to this particular diagram, and then ask yourself that from, can you interpret this entire database design? So if you're able to do that, then you will be able to use that knowledge specifically for your project as well, and any other assignment that you will be dealing with later on, which requires you to interpret an ER design. Okay. So now that we understand that, let's do that. Okay. So first of all, let us start with the attributes. So attributes are basically a set of characters, a character or a set of characters, character or set of characters which can be alphabetical or numeric or both. Okay, which defines a certain property of an entity instance, or we can even say entity. Okay, we are using it in a bit of an overloading fashion. We are using the terminologies, but you get the idea. So that means if you have students as your entity, then what are the different fields or what are the different attributes that defines this entity students or student? Okay, so you can basically have student ID, you can have student age, you can have student contact, you can have student name, and so on and so forth, right? And you can add even more attributes to it. So let us look at the different types of attributes that are supported by the ER model, okay, in the ERM, which you have to account for when you are developing a database design, right? So the first one, the very basic one that you have to evaluate is required versus optional. Okay, so very straightforward. Okay, as the name suggests intuitively, is the attribute that you are defining for an entity, is it required or is it optional? So that means, do you need to have some value present for those attributes, or can you leave it null? Okay, so basically what this translates to is, must there be a value specified, or can you leave it null? Okay, so remember, null is not a value. Okay, it signifies the absence of value. So if you see something which is null, it's not like, putting zero. Zero is a value itself, right? But if you just say it is null, then it just translates to the fact that there is no value present for that particular field, okay, or for that particular attribute. So within the MySQL Workbench environment, so if I just say in Workbench, this whether the attribute is required or optional is specified by checking the not null box. So remember, there was an NN box which was saying not null. It basically stands for not null. So if you check the not null box, then that signifies that the attribute is required. That means you must specify a value for it. You cannot leave it empty. And if you do not check the not null box, then basically it is optional. Okay. So now if you can look at this example here, so this way of writing a particular entity where you have the name of the entity and then within first brackets you specify the different attributes that belongs to that entity or that defines that entity, and then you underline the primary key. This is basically known as a relational notation. Okay, so this way of writing a database table is known as a relational notation. So in this, remember, primary key is always going to be not null, because otherwise it will violate the entity integrity rule. But everything after that is up for debate based on the requirements of your policies, okay, or your function requirements and stuff like that. Do you absolutely need to have an age, or can you leave it as an optional field? Do you absolutely must have the students specify a contact information, or can you leave it blank? Do you absolutely must have a student specify a name, or can you leave it blank? Right? So these are some of the discussions that you need to have with respect to required versus optional. And any and every attribute that you kind of establish, you need to think about this fact that whether that attribute is required or optional. Okay. A general rule of thumb that I will give you, it's not a rule of thumb because it's not specified as such, but it's more of this kind of hack, so to speak, is that if an attribute is involved in any kind of arithmetic operation based on your understanding of your functional requirements and your data transformation requirements, then it is better to declare that attribute as required. Because later on, when we go to SQL, we will see that there are some operations known as aggregate functions, which allows you to perform different kind of arithmetic operations like sum, or finding the max, the min, the mean value, and so on and so forth. So if you apply those on attributes which are optional, then it's going to give you some skewed results or some incorrect results. So always keep in mind in the back of your head that if an attribute is going to be involved in any kind of arithmetic computation, then it is better to declare it as required, so that even that if there is an empty value, you assign it with a flag value, like a 0 or something, and then you can write a conditional statement to say that, oh, if it's 0, then ignore that value, or 0 is not going to have an impact overall in the entire computation. Okay. So that is some forward knowledge that you need to have about your attributes. Okay. So from, again, just a quick note. So from your SQL environment, if you go to this model, if I add a table, all right, whatever the table, and if I add a column name, so this is the required versus optional field, the not null field. Okay, that this is how you can specify required versus optional. So that was the first one. So the second one is simple versus composite attributes. Okay, these are pretty straightforward. You just have to understand and recall a lot of them, right? So simple versus composite attributes is if you cannot break down an attribute any further in terms of its value, right, then it's a simple attribute. So that means if an attribute is simple, you cannot break it down any further. So examples of such attribute would be your student ID, okay, your student age, because think of the value that student age will have. It will have value like 21, 22. Can you break this down any further to make any meaningful sense? Not really, right? Student name, however, in this way of implementation, the question for you is it a simple attribute or is it a composite attribute? So if you have guessed that if if a simple attribute stands for an attribute which cannot be broken down further to make any meaningful sense, composite attribute is basically an attribute which can be further decomposed. Okay, so that means student contact information could be an example of a composite attribute, because then if the contact is an address, okay, so then you can further break down the address into street number, city, state, and zip code. Right? So I hope you understand the difference between a simple attribute from the examples versus a composite attribute. So going back to our previous question, in this particular implementation of this relational entity, would you categorize student name as a simple attribute or a composite attribute? Okay. And the answer should be a resounding composite attribute, because you can take the student's name and you can further break it down into first name, last name, and middle name. Or even initials. So you can relate to this example practically by thinking of all those web forms that you might have encountered when you're registering for an account from time to time in different websites, right? Especially government websites, where the form where you enter the name, right, when you're creating, is broken down into first, middle, and last, and then you have a drop-down option where you can select whether your initials are Mr., Mrs., and then if you have a suffix, junior, senior, so on and so forth, right? Have you ever wondered why that is broken down as such? Because that is being fed directly into the database in this particular fashion. So then the next question is, in terms of practicality of your design, why do you need to consider this? Why do you need to consider whether an attribute is simple or a composite attribute? Well, if it is simple, you don't have to really do any kind of deliberation. You don't have to put any thought process about, okay, it is simple, what should I do? No, there is no what next after that, because you cannot break it down any further. What you actually have to pay attention to is whether the attribute is composite, and do you need to break it down further depending on the requirements of your data transformation. So what that means is that if you're going to have database queries that will require you to identify or extract data records or data rows based on, let's say, solely on the state or solely on the zip code, then you should not have contact as a composite attribute. You need to break it down such that it kind of simplifies the process of writing your SQL queries. Okay, so that is the idea, and that is why you need to evaluate whether an attribute is composite and whether you need to break it down further to create new entities. So that means here student contact was a composite attribute. So now if I break down the composite attribute into its simpler attributes, that is street number, city, state, zip code, and even country, if you are working on with an organization that handles global businesses, right? So then you can see that this one attribute now is broken down into 1, 2, 3, 4, 5 attributes. So this initial example, which had 1, 2, 3, 4 attributes, will now have 1, 2, 3, and then 5 more, 8 attributes. So you see it kind of improved your design further. So that is the goal of these kind of assessments, and that is why we are going over it. Okay, so that was the second one. So the third one is single valued versus multi-valued attributes. So single valued means if attribute can have only a single value, at any given time period. Okay, so that means student age is an example of single value, because at any given time there is going to be only one single value for age of any given student. You cannot have a student who at a given point of time their age is 23 and 21 at the same time. That would be some science fiction stuff. Okay, I think there was a movie as well, I forgot, but there was an assassin who was sent from the future to kill his old self, and something along those lines. I forgot the guy. The actor in that was one from the movies Die Hard. I forgot his name as well. Bruce Willis. Bruce Willis and the guy who plays Robin uh, in Dark Knight 3. I think those were the two actors. I forgot what the name of the movie is. Anyways, I digress. So coming back to the point, student age is an example of single valued attribute, right? Similarly, student ID is also an example of a single valued attribute. Okay, because the goal is, or the definition is, the attribute can have only a single value at any given time period. Okay, so just going by the definition of single valued, multi-valued will be the exact opposite. That means the attribute can have multiple values at any given time period. Okay, so now what are some examples of multi-valued attribute? So think of this for a second. From any domain, you can choose any domain, you can choose any entity. You don't have to stick with the current example that we have. Uh, and try to ask yourself what it means, and does it make sense? Okay, so from our example, in the student example, there could be different, you can take or make attributes which are multi-valued attributes, right? If there is an option for, let's say, student certification, okay, we can say that student course could be an example of a multi-valued attribute, because at any given time period a student can take multiple courses. They can take, let's say, CSI 1002, CSI 3434, etc. Right? But necessarily we won't be implementing student course as an attribute. But the intelligent part, or the intuitive part of all these design steps, is that even if you did end up considering student course as an attribute, it will come out as an entity. Okay, and it will take you back to this scenario here, where course is basically represented as an entity and not as an attribute. So that is what the kind of like the clever way these things have been established, such that even if you did make that misstep of classifying course as a student attribute in order to kind of represent the different courses that a student can take, the way these things are set up, it will actually bring that out and then make an entity out of it, right? However, in this particular instance, you naturally will not represent course as an attribute of student, okay? It's just going to create some like functional requirement problems at the end of the day, right? But student certification could be if you have certificates on, let's say, a data science program, right? You can also have a certificate in cybersecurity. You can have certificate on Java development. You can have certificate on MySQL development and stuff like that. But what the core notion that I'm trying to relay here is that an attribute which can have different values at any given time period is known as a multi-valued attribute. Remember, this time period information is important. Okay. Otherwise, what can happen is, let's say if I tell you that there is an attribute called product. Okay. So then the product will have or an entity called product, and then an attribute called product price. So then what is product price? Is product price going to be a single valued attribute or a multi-valued attribute? So if you don't bring the time period into the picture, then it is kind of confusing to figure it out. Because let's say in 2015, the price of this product was about $300, right? And then in 2019, let's not talk about 2020. The price of this product is let's say $450, something like that. So does that make it multi-valued attribute? No, it's still a single valued attribute, because at any given time period it had a single value. Okay. However, in 2015, if the price of this product had different values, then product price would have suddenly become multi-valued. But that generally doesn't happen in a practical environment, right? So you get the idea. So then the question is, if you have a multi-valued attribute, how are you going to implement it? Okay. So that is what the question that we are trying to address is, then how to implement. Because design is all good, but remember, the design will translate to the code which will be used to implement the database environment, forward engineering, right? So we just don't have to conceptually discuss this, we also have to discuss it from an implementation standpoint. So how to implement it? How to implement multi-valued attributes? That's the bigger question. So now I can offer you two ways to do it. One is the naive way, and then one is the more efficient or the intelligent way that will reduce the inconsistencies in your database design. So similar to your multi-valued attribute or composite attribute, you can break it down into its individual values or individual components, right? So that means the first way that you can do, let's call it the brute force, is you can try to store all the values by expanding it. But this is creating a problem that we are very familiar with. It's going to create a problem of structural dependence. And the reason why is because if you have student certification and if you want to expand all the values, let's say these 4 values, then how are you going to implement it? Then you will have to do student certification 1, comma, student certification 2, comma, student certification 3, and then student certification 4, right? But you can immediately recognize the implications of this design. This is a very poor design. And the reason is because every time a new value comes into the picture, you will have to change the structure of your database table, not the database, but the table of the database, right? And additionally, if this is the max value, or if this is the upper bound of the values that you currently have in your database, if a student doesn't have all these certifications, then for that particular student, some of these attributes are going to be null. And that is going to create, again, problem with null values, right? In terms of your assessment and stuff like that. Some students might not have exactly these same set of certifications. So you may have to include more certifications or different types of certifications, right? If a student graduates from the university, then you will lose that record of that certification, which might have been uniquely held by that student, but you would like to keep it on record, right? So all of these will create a problem or create multiple problems, which essentially boils down to the issue of structural dependency. So then it is doable, but it is a very static way. That is what is meant by this brute force method, that yes, it creates structural dependency. It kind of takes us back to the era of file systems, right? But that doesn't mean that the file systems were not functional. They were functional, but they were functional in a static way. And if you had to change them, then there would be a period of downtime where all the changes have to be taken or made implemented, and then it is back up online again, right? But in this day and age, no businesses can kind of can I forgot the word. No businesses can do that. They don't have the breathing space. I don't know if that's the most accurate term, but they don't have the breathing space to allow that to happen, that their company website is down for a good period of time because they're just changing the structure of one table because some one record or 3 or 4 records had to change the number of values that it can take for its attribute, right? So this is something we can say as static. It's a static way. So the other way is the more intelligent way, or the dynamic way. Is to store the multivalued attribute as an entity and create a relationship with the parent entity. So what this means is that now, instead of having it as an attribute, so instead of within the student entity, instead of having this multi-valued attribute called student certification, and then other entities are also present, what we're going to do is we're going to take this out and create an entity out of this. Okay, give it some primary key, give it the value of the certification, that is, let's say, type of certificate or certificate name, and then add some more relevant attributes like date obtained or certificate date, certificate expiration, and then add a foreign key to it that will allow us to trace back that this entity belongs to this parent entity, which is student. So now, instead of doing this, what we end up having is we have the student entity and then all the attributes that you have, and then you have a primary key and so on and so forth. Okay, so you don't have a line here, and then you have the other entities, right? So now you take this out, and since it is a multi-valued attribute, right, it is always going to be 1:m, and then we can add certificate here, create a primary key, add the foreign key of the one side in the m side, and then add any other relevant attributes for this particular entity. So now you can see how our database design can evolve just by looking at the type of attributes. Because this was originally an attribute in this entity. It was not an entity based on any kind of functional requirements, but in order to make your design more robust and understanding the concepts of the ER model, we just ended up with a new entity altogether. Okay, so this is what you have to keep in mind. So just a forward reference, when you are doing this kind of relationship, okay, that is when you are bringing out a multi-valued attribute from a entity and then creating an entity of its own and then joining them with a relationship interaction, this line is always going to be a solid line. Okay, and we will talk about why when we talk about the different types of relationship strength and what are the different types of entities that you can have. Okay, so this is single valued attribute versus multi-valued attribute. Okay, so then the final attribute I think it was 1 required versus optional, 2, 3, 4. 4. So the fourth one are derived attributes. Derived attributes, you need to assess them for data redundancy purposes. That is why you need to assess your design to see if you have derived attributes or not. Derived attributes are similar to age. Assuming you are also storing the value, age will be a derived attribute if I assume that I also have a field within this table which is student date of birth. Because now you can invoke the SQL inbuilt function called year and then subtract it with the student date of birth. So that means you can perform a relational operation in order to compute, sorry, not the date of birth, but the age of the student. So that means this attribute can be derived from another attribute which is present in the same table or in a different table, and then using some relational operations we can regenerate this value. So that means as per the definition of data redundancy within the database environment, this or all the derived attributes are actually redundant. So what you need to discuss or what you need to evaluate when you're looking at derived attributes is whether this derived attribute is present to support or assist the database in terms of its performance. Is that why you are keeping the derived attribute? So an example for database performance will be student GPA, because you can always compute the cumulative GPA by looking at all the courses that the student have enrolled, and if you're keeping track of the letter grade that they have received, and then transforming what is the corresponding point for that letter grade, and then doing the overall evaluation. So in that sense, GPA is also a derived attribute. But if you have to do this all the time, every time somebody queries for a GPA for all the students and to create the cumulative reports and stuff like that, it kind of becomes counterintuitive, right? So this is one way of storing the database performance. And the second one, if you remember, was to preserve the historical accuracy. But historical accuracy in this case is not applicable, because it does not necessarily apply to derived attributes. Okay, so if you're just looking at derived attributes, then the question that you will be asking yourself is that, are you keeping that derived attribute for performance purposes? Because if not, then you don't need it. You're just creating an additional attribute in the table that you have to implement, you have to keep a track of. It doesn't make any sense. Okay, so this is basically all the different types of attributes that you have. So let's come to the next topic, which is entities. Okay, so the different types of entities that you can have within the ERM model. Okay, so there are two types of entities that you can have. One is a strong entity, okay, and the other one is a weak entity. And these are kind of driven by the concept of existence dependent, or not dependent, but dependence. Okay, so what that means is that if the existence of an entity in the database environment or in your database environment is completely dependent on another entity, so, or if you want to rephrase, we can say that an entity cannot exist in the database if it is not in a relationship with another entity, then that entity, this entity, is said to be existence dependent on the other entity, right? So strong entities, as the name suggests, are existence independent. Okay, examples for strong entities will be students. Okay, you can have professors, you can have courses, and then so on and so forth. If you can think of any more examples, like in your domain, you can also think. And then weak entities are entities which are existence dependent. Okay, so what that means is that they can only exist in the database if they are in a relationship with another entity. So example of that will be classes. So that means classes are for a particular course, and I'm talking about class sections, right? The different sections of the course that you offer. So there won't be any classes of a particular course offering if there are no courses to begin with, right? Then any kind of linking entity, which are basically used to a bridge entity or associative entity, there are different names for it, right? So used to implement M is to N relationship, right? So they're all existence dependent, right? Similarly, multivalued attributes implemented as entities are all weak entities. Okay, and so on and so forth. So you can think of other examples as well, and it's kind of I hope it's kind of clear as to what the difference between these two components are or subcomponents are based on this definition of this concept of existence dependence. Okay, and that is all there is to entities. There is no kind of differentiation in that. Oh, so quick note is that in terms of your ER design here, for required and optional entities or attributes, you use bold font to represent required attributes in crow's foot notation. Okay. Simple versus composite attributes, they don't have any kind of representation in crow's foot. There is also another representation or a notation which is known as the Chen's notation. Okay, but I leave that to you as a self-study. Okay. So, and please do learn it. Just because we don't have any exams, don't just let it go. Otherwise, you will be at a loss. So just learn and skim through it, know what the differences are. So in case if any company is specifically following Chen's notation, then you can use it, but mostly they don't. Okay. So simple versus composite, there is no representation in the crow's foot notation as such. Single valued, multi-valued, there is no representation as such. Okay. So that is the only, for derived attributes, you don't have any notation as such in the crow's foot notation. For strong and weak entities, distinguishing between them, there is no notation, but the representation comes from the relationship, and that is what we are going to discuss next, is the relationships. Okay. So relationships in ERM. So now, as far as relationships are concerned, there is various different categories of relationship subcomponents that you have to address. Relationship is the most complex out of all these three categories. Attributes, 3 different categories, done. Entities, 2 different categories, done. Relationship needs to address a lot of different aspects, as any relationship does, right? So as a result of that, the first thing that you need to keep in mind, that when we are within the realm of ERM, the relationship type or the relationship classification is actually called a connectivity. Okay, so that means you know that the different types of relationships are 1:1, 1:m, and logical m:(n). So that within the ER design realm is known as connectivity. We don't necessarily call them as relationship classification. So remember this. If somebody asks you what is the connectivity between entity 1 and entity 2, they're actually asking about the relationship type or relationship classification. All right. After that, you have cardinality of a relationship. So I will just say cardinality of a connectivity. Oh, no, connectivity stands for that. So we just use relationship. Okay. So cardinality is basically the lower and upper bound of entity instances. So that means, let's say if you have this, you have professor, and then you have student. Okay, our trusty example. And then the relationship is basically, so I will start doing the proper notations from now on, such that we can relate to why later on when we actually discuss it, you can start relating to why we have been doing it this way. Okay, so then this is advices. So cardinality kind of establishes that if a professor advises student, what is the minimum number of student that the professor advises? Let's say not lower and upper bound, that is becoming too algorithmic. Minimum and maximum values of entity instances associated. Okay, so that means here the cardinality is asking what is the minimum number of students that a professor will advise, and what is the maximum number of students that a professor will advise. So here we can see that this is saying, just from the notation, just looking at the notation, we can say that the professor is going to advise 1 to m students. But what the cardinality is forcing us to specify is what is this m value. Okay, so you have to separately write that the professor will advise from 1 to 6. So if you see in a crow's foot notation, this value 1 to 6, what it represents is that a professor is going to advise a minimum of 1 student and a maximum of 6 students. But remember, you have to also accommodate the bidirectionality of a relationship. So that means if you have addressed the cardinality on one side, you will also have to address the cardinality on the other side. But here, if you look at the notation, this stands for 1. Okay, so this is the one side. So that is why that double dash line is coming into the picture. It states that a student will be advised by one and only one professor. So the minimum number of students that a student will be advised by is 1, and the maximum is also 1. Okay. So remember, when you are writing your business rules, these are kind of the things that you will have to specify. That is, you need to break down your business rules into 2 portions. One, like if you want to make it more formal and understandable for your clients or your bosses or your managers, you will have to break down the business rules into connectivities, and you have to break down the business rules into cardinalities. So these are the 2 things you will have to write for business rules. So for each relationship, you will have to write a pair of connectivity rules and a pair of cardinality rules, okay, to make it more understandable and easier conversion to the diagram. All right. So that is what cardinality stands for. Okay, so we did connectivity, and connectivity is straightforward, so I'm not going to discuss it again. We have already talked about it in details many number of times before this. So cardinality, connectivity, and then let's talk about relationship. While we are on the topic already, relationship participation, because that has a direct implication on the notation of the crow's foot diagram or the crow's foot notation. So relationship participation are of 2 types. One is optional and 2 is mandatory. Okay, so as the name suggests, there may or may not be association with the other entity, and there has to be at least one association with the other entities. Okay, so that means if there is optional, so that means the foreign key value can be null or may be null. But if it's mandatory, then the foreign key must refer to a valid primary key. So in terms of crow's foot notation, let's say if our business rule was, an instantiation of our business rule was that a professor may or may not advise a student, okay, and a professor may advise up to m students, or a professor may advise multiple students. Okay, so now just for this one direction, you have not the band one direction, the one direction in the relationship. Okay, then you have 2 business rules already. So then your pair of business rule is becoming actually 4 business rule for a single relationship if you have to specify the relationship participation. Okay, so this is good. Our design is becoming more and more stringent. Okay, so if that needs to be represented, if this aspect needs to be represented using the crow's foot notation, then your diagrams will start becoming like this. So professor, and then we have so again I made the mistake. This will be dotted line, and then you have the student. Okay, so this circle here stands for optional participation. And now your cardinality will also start to change. Instead of 1, 6, this will become 0, 6. And this will remain as 1, 1. However, in practically speaking, can a student be advised by somebody other than a professor? Yes, you can have a staff who can advise. You can have the graduate advisory staff people advising the students as well, right? So that means you can have the optional participation here as well. So they may advise 0 or 1 students, or a student may be advised by at least one professor or not a professor, somebody else. Okay. So that is what these what do you call these circles and these solid dashed lines represents in the participation. So if you have this, okay, then this stands for 0 or M. Okay. Thereafter, if you have this, then this stands for mandatory participation for 1:M. And then if you have this, this is mandatory participation for 1:1. So this will be 1:1. And then if you have this, then this is basically 0 or 1. Okay, so this will not be in this format, but this will be like this, and then dotted arrows from here. So now you understand what these circles and these dashed lines are representing here. So if you take any particular example, let's say this one, okay, that a professor may or may not be the dean of a school. Every professor need not be the dean of a school, right? But there could be one professor who is the dean of a school. However, the dean of a school has to be a professor. Nobody else can be a dean of a school. So in the bidirectionality aspect of is dean of, the relationship label is dean of, in this direction, the participation is mandatory. But in this direction, the participation is optional. And as a result of that, this is what the crow's foot notation is representing accurately. Okay. So now you can look at this one here. Department employs professor. Okay. So that means a department must employ at least one professor. A department cannot be a department if there is no professor in there, right? Then who is going to teach the courses? So that is why the participation of this relationship in this direction is mandatory, and that is how it is represented with a dashed line and then the M sign. And then in the bidirectionality, the professor must be employed by a department. Otherwise, they are not a professor. They will be a staff. Okay, they must belong to one department. So in the opposite direction, you also have mandatory relationship participation. Okay, so that is what the relationship participation indicates. Okay, so thereafter, so now we have covered connectivity, cardinality, relationship participation, and its notation in the crow's foot design or crow's foot diagram. Okay, so then the next one is relationship strength, GTH. Okay, and again it is of two types. One is weak or non-identifying relationships, and the second one is exactly the opposite, which is strong or identifying relationships. Okay, so let's take the first one, which is the non-identifying relationships. Okay, So let's say if you have these two entities again, professor, and then you have, let's say it is mandatory for the sake of without any loss of generality, and then you have student. Okay. So now, of course, this dotted line now stands for non-identifying relationship, and the concept behind non-identifying relationship is that in a relationship like this, and you will always read the relationship from left to right, not the other way around. Okay. So that means in such a relationship, this entity is known as the parent entity, and this entity is known as the child entity. Okay. So here, what non-identifying relationship is based on the concept that if the primary key of the child entity is not composed of any portion of the parent's primary key, then their relationship is weak or non-identifying. Okay. So if you want to visualize this concept, what is the primary key of the student? The primary key of the student is student ID. What is the primary key of the professor? The primary key of the professor is professor ID. Okay. So here the foreign key is professor ID, because that is how you're going to implement this 1:n. So to rephrase this concept, if the primary key of the child is not composed of any portion of the foreign key, then the relationship between the parent and the child is basically a weak non-identifying relationship. Pretty straightforward. Okay. So that is basically the concept of non-identifying relationship. So now if we look back at our diagram, okay, you can see that all the dotted lines, this concept applies. In this relationship, professor advises student. Professor is the parent, student is the child. Okay. The primary key of the child, we just discussed this. So it's kind of moot to discuss this again. Let's take this one. Professor is the dean of a school. The primary key is school code, and the foreign key here is professor number. The foreign key, partially or completely, does not play any role in the primary key of the child entity. And as a result of this, you are representing a weak non-identifying relation using a dotted line in the crow's foot notation. Okay. Now let's look at another example, which is strong relationship. You can see here, class is found in enrollment. Okay. So here class is the parent and then enrollment is the child. Okay. So here the child's primary key is composed of a foreign key partially, which is coming from the parent, the class code. So as a result of that, the relationship between them is a strong or identifying relationship. Okay. So you can go with another example here. Between class generates course. Okay. So the foreign key is the department code, but the foreign key has no role to play in the primary key of the course. In addition to that, the primary key of the parent is class code, but it has no role to play in the course. I just made a mistake. It's the other way around. I didn't read it from left to right. Remember, left to right. So in this way, the left to right is in this direction, unfortunately, because course generates a class. That's what this relationship label is signifying, not the other way around. Okay. So this is what can happen if you read the relationship in the reverse direction. You can make a lot of mistakes. Okay. So course is the parent and then class is the child. So the primary key of the child has no component of the primary key of the parent, and as a result of that, their relationship is weak. Now the question is, if we had changed the primary key of this child to include course code and class section to be a composite primary key, then you can still uniquely identify all the rows in class. And if that ends up happening, that means the primary key of the child now has partially a component of the primary key of the parent. And then this relation will now suddenly be transformed into a strong identifying relation. Okay? So let's look at the definition or the concept of strong identifying relation. So I'm hoping that my picture is somewhere here. I generally can't see it. So I will ignore this area and try to write it side by side so that we can understand it. So strong is identifying relations, okay, or strong relations. Okay, so there are two conditions that needs to be met for a relationship to be an identifying relationship. Okay, the child entity has to be existence dependent. Okay, so in other words, the child entity needs to be a weak entity. And the second thing that needs to satisfy is that the primary key of the child should be entirely or partially be made or designed with the primary key of the parent. Okay, so this is denoted by a solid line in the ER diagram, and this is represented by a dashed line in ERD. So now you have the answer to the question as to why in this palette there are two different types of options for the same relationship. So that means if you want to establish a 1:1 between a 1:1 non-identifying relation, then you use this. If you want to establish a 1:1 identifying relation, then you use this. Okay, so that clarifies the design process as well. All right, so moving on. So we have done relationship strength, classification, cardinality, participation, relationship strength. Let's talk about relationship degrees. Okay, so in terms of relationship degrees, you can have three types of relationship degrees. The first one is a unitary relationship, a binary relationship, and then a ternary relationship. And this is conceptual. Okay, because you need to make changes to it in order to implement it directly. Okay, so unitary relationship is basically an entity in a relationship with itself. Okay, so that means if you want to take an example, let's say the relationship label is, let's say, course prerequisites. Okay, you want to set up course prerequisites. So you know the fact that you're going to store all the courses in one table. Okay, so now if you want to create course has prerequisite another course, then that becomes redundant because you're implementing it. So you have to implement the relationship of this relationship with the same entity, right? So in order to do that, what is the connectivity for this? That is the first one. So the connectivity in one direction is a course can have, let's write down the business rules. So course may have one, let's say a course may or may not have one or more courses as prerequisite. Okay, so I just plugged in the cardinality as well, just for the sake of completion. Okay, and then in the bidirectionality of it, we can say a course may or may not be the prerequisite to multiple courses. So then what is this? This is basically a m is to n with a optional participation. Okay, so now if we have to implement that, we will have this, whoops, and then this, and then we will have this. So we will have two crow's foot. So now the question is, what is the relationship strength? Okay, we have figured out the connectivity is m is to n. The participation is optional, and from optional you can also do what is the cardinality. Okay, so if you want to be more rigorous with respect to the policies, you can say 0 and then a particular value, but now we can just say 0m and 0m. We have done that. So the only thing that remains, and the degree is unary, we are discussing this. So it is a unary degree. Now the only thing is strength, relationship strength. What is the relationship strength? Okay, so at this point, pause the video and try to answer what the relationship strength is going to be. Okay, welcome back. So now the relationship strength based on the definition of relationship strength is going to be a weak or non-identifying relationship. So this is going to be non-identifying. Okay, and I hope you all got the same answer as well. Why is something I leave it to you as a self-study or a self-exercise. It's pretty straightforward. Try to look at this concept definition here, that what is a non-identifying versus what is an identifying, and then try to extend that understanding to this particular instance. Okay, it's pretty straightforward. If you cannot, then talk to me and then we can discuss it again. Okay, so this has prerequisites. Okay, so this is an example of a unary relationship. Okay, of course you will need to have a linking table in order to implement this relationship, because it is basically m is to n. All right, but otherwise if it was 1 is to m or it was 1 is to 1, then you can implement it directly. And when I say directly, you can basically add another column in this particular table which will repeat the primary key, but this time as a foreign key. Okay, so try those things out. Self-exercise basically is how will you implement So unroll this in terms of a relational table, and then you will see that it becomes quite self-evident as to how you will implement it. Okay. So thereafter you have binary relationships. Just a quick note before we go any further. All unitary relationships will end up being weak non-identifying. Okay, so I will give you the hint that all the relationship strength of any unitary relationship degree is going to be weak. Okay. So binary relationship is again a relationship between two different entities. So that means if professor advises a student, then this is basically a binary degree. Okay, bi meaning two, so that means if a relationship is between two entities, then that kind of relationship is binary. Okay, so we can just put this here and it becomes a smiley after that. Okay, and then you have ternary degrees, so that is more than two. So ternary degrees are basically relationships between three entities or more, right? But it is mostly conceptual, or not mostly, but it is conceptual, right? So in order to implement it, you have to add more tables in it so that you can actually implement it, right? So you don't have an example of a ternary relationship in the university domain. Can we come up with a ternary example? Let's try to make one. If not, then I will just use the book to explain it. Okay, but let's give it a shot and see if we can come up with one. So let's say professor and then books and then bookstore and then student. Okay, so I think we might have something on our hands. Okay, so professor, let's say, assigns books. Books are, or a bookstore, how will it be? Will a book keep the bookstore, or a bookstore will keep the books? I think it's a bookstore that will keep the books. So let's say we only have one Barnes and Nobles, right? Yeah. So this will have multiple books. Okay. And then students, so this will go in this direction as well. So students will loan different books. Okay, so either purchases, or if the context is loaning, then you can just say loan. And bookstore has or keeps M books. Okay, so this is basically a relationship between professor, bookstore, and student. And I brought in this entity, which we will call the linking entity, that is actually used to implement the conceptual relationship between professor, bookstore, and students. Okay, so the process is purchasing books, okay, or assigning books, or course textbooks. So if you want to explain this in a conceptual way, you would have drawn something along the lines of professor assigns course textbook, and then you will have bookstore, and then students. Okay, so you get the idea of a ternary relationship. So this is the conceptual representation of the ternary relationship. And then if you want to, oh, does it actually take to the next slide? No. And then the actual implementation is by using a linking entity, which is books. So now you will be able to implement this in your database environment. Okay. So another note is that all unary relationships, where is my unary relationship? Okay, here. So all unary relationships are also known as recursive relationships. Okay, and the connectivity can be 1:1, 1:m, or m:n altogether. Okay, so that is what we will be. That is another way of keeping track of the unary relationship degrees. A good question. So you understand the recursive relationship. It is in a recursively, it is in relationship with itself. Can you have recursive relationships for binary or ternary? Think about this. Okay, if you can come up with it. So now, knowing all of this, so this kind of completes the relationships or the different components of the relationship. So just to recap what we had, since we did it one by one. So the different components, when you are evaluating of relationships, or let's say ER diagram relationships. So the different components that you have to evaluate when you are looking at relationships, the first one is basically the connectivity. Okay, that is what is the type of relationship. The second one is cardinality. Okay, there is a minimum and maximum association. Then you have the relationship participation, which is whether the relationship is going to have optional or mandatory association. Then you will look at the relationship strength, okay, which is going to be either non-identifying, that is weak, or identifying, which is strong. Okay, and then you will have relationship degree, that is whether it is going to be unary, binary, or ternary. And unary relationships are also known as recursive relationship. Okay, and another quick note here is any relationship with a linking entity. So what are linking entities? Linking entities are also known as composite entities, okay, or bridge entities. So they are basically used to implement conceptual relationships. So that means relations like m:n, or if you have, let's say, ternary relationships. So in all these cases, or if you have multivalued attributes, So in order to implement all of these, you need the help of what is known as linking entities, composite entities, or bridge entities. The reason why I'm not calling it a composite entity, because there is a good chance that you will confuse a composite entity with a composite attribute. They're two different things. So that is why I keep on saying linking entities. So you can relate to the fact that it is actually linking two different other entities, right? So any relationship with a linking entity is identifying. Okay, so that means it's going to be a identifying strong relationship. Think about this. Look by looking at the ER design diagram and see if you can concur with this statement. Okay, so that is it. So as a self-study, read the last portion of your chapter 4. Read the last subsection of chapter 4 from textbook. Okay, so what will happen is that it will guide you through the business rules of this particular ERT. Okay, and then it will help you understand how, using all of these components that we discussed, we ended up getting this diagram. But if you look at it in a simple glance now, after learning all of this thing and then after revising it a few more times, then you will be able to decipher what is going on in this diagram, okay, and what you need to do. And then you can extend that knowledge to your project and then prepare your ERD as well. Okay, so that is basically that's all there is to chapter 4. Pretty straightforward. Okay, so that is the conclusion of entity relationship models and the different components in entity relationship model. In the next lecture video, we will talk about the enhanced entity relationship model, okay, which is known as the EERM, and using the EERM, how to draw the EERD, or the enhanced or the extended entity relationship diagram. It's a special feature, and everything else remains the same compared to ERM. But what is new here is basically the concept of attribute inheritance. Okay, so basically we are introducing the idea of object-oriented programming into database design. Okay, so that is what we will be discussing in the next lecture video. So I'll see you all again in the next video. Until then, stay safe and take care.